What Voyager has discovered and achieved so far. We thought that once we passed the Hercules Columns of the heliosphere, the probes would stop talking to us. Not because of the energy exhaustion, but because from then on we imagined a desert, the interstellar space, almost completely empty of matter and therefore also of physical phenomenon to detect and to tell. Far from the protective embrace of the sun, the boundary of our solar system seems in fact to be a cold, empty, and dark place. A vast expanse of frightening nothingness. But we were wrong. The Voyager probes have left the solar system behind, but the great void they had in front of them is instead proving to be an inexhaustible source of new phenomena. History. Launched in 1977, the twin spacecraft Voyager 1 and Voyager 2 were part of NASA's ambitious mission to explore the outer solar system and beyond. The two probes were designed to take advantage of a rare alignment of the outer planets, allowing them to visit Jupiter, Saturn, Uranus, and Neptune. Voyager 1, which was launched on September 5, 1977, took a faster trajectory, while Voyager 2, launched on August 20, 1977, followed a longer path that allowed it to visit more planets. Voyager 2 was the first spacecraft to fly by Jupiter in 1979, followed by Saturn in 1981, and then Uranus in 1986 and Neptune in 1989, making it the only spacecraft to visit Uranus and Neptune. Voyager 1, after passing Jupiter in 1979, made a more direct course towards Saturn, where it performed its flyby in 1980. Voyager 1's trajectory enabled it to exit the solar system at a faster speed, allowing it to become the first human-made object to reach interstellar space, crossing the boundary of the heliosphere in 2012. Both spacecrafts' primary mission was to study the outer planets, but after completing their planetary flybys, the probes continued on their trajectories, eventually entering the region beyond the solar system influence. In 1990, after passing Neptune, Voyager 1 turned its camera back toward Earth and captured the famous pale blue dot image, showing Earth as a tiny speck in the vastness of space. After completing their planetary explorations, both spacecraft continued to transmit data back to Earth. In 1998, NASA officially ended the Voyager spacecraft planetary mission, but continued to communicate with them for scientific data as they ventured into the outer reaches of the solar system. Over time, both probes left the area dominated by the solar wind, crossing the heliopause, the boundary marking the edge of the solar system and the beginning of interstellar space. Voyager 1 crossed this boundary in 2012, and Voyager 2 followed in 2018, marking the first time that human-made objects entered interstellar space. Despite their incredible distance from Earth, tens of billions of kilometers away, communication with both probes is still maintained. The Deep Space Network, DSN, a series of antennas across the globe, is responsible for maintaining contact with the spacecraft. The signal from the Voyagers is incredibly weak, taking over 21 hours to reach Earth at light speed. But both probes continue to send back valuable data from interstellar space, providing unprecedented insights into the environment beyond the solar system. The Voyagers carry a unique message from Earth, the Golden Records, which contain sounds, images, and music meant to represent humanity and planet Earth, intended for any potential extraterrestrial life that might come across them in the distant future. As of today, both Voyager spacecraft continue their journey farther into interstellar space, with Voyager 1 being the farthest human-made object from Earth. Their missions, which were initially expected to last only a few years, have now stretched into decades, and their data continues to provide valuable insights into the farthest reaches of the universe. Cosmic Tsunami. For quite some time, they both have been going beyond the heliopause, the no man's land between the heliosphere, the bubble of hot solar plasma that encloses our entire planetary system, and the region that surrounds it, dominated by the interstellar medium. A region that Voyager 1 has already reached in 2012, and Voyager 2, which followed a different and longer path in 2018. Over the past century, scientists have managed to understand the composition of the interstellar medium, largely through observations using radio telescopes and X-ray telescopes. They revealed that it is composed of extremely diffused ionized hydrogen atoms, dust and cosmic rays, interspersed with dense molecular clouds of gas that are believed to be the birthplace of new stars. But knowing the components of a soup is not the same as knowing how it tastes. You have to go there and taste it, as they are doing in this moment, the two probes which are experiencing completely new phenomena in an environment not reproducible in laboratories. Not long ago, Voyager 2 revealed that the density of cosmic rays from beyond, specifically the interstellar wind impacting the outer edge of the heliosphere, was much higher than previously expected. Another discovery also brought attention to the wind blowing behind the probes, which carries a steady flow of electrons from the Sun into interstellar space. While our Sun is relatively calm compared to some of the more volatile and dangerous stars in the galaxy, it does occasionally release enormous bursts of energy. These outbursts expel ionized plasma particles that rapidly spread into interplanetary space, resembling a cosmic tsunami, a shockwave traveling outward from the Sun's surface, propelled by the solar wind. Something similar happened in 2014, when a giant solar flare kicked off a huge particle stream. The explosion crossed the orbits of Mercury and Venus at nearly 800 kilometers per second, and after 2 days it reached Earth, fortunately protected by its solid magnetic field. The next day it hit Mars, and the day after it swept through the asteroid belt, continuing towards the gas giants Jupiter, Saturn, Uranus, and after more than 2 months, Neptune, 4.5 billion kilometers away from the Sun. 6 months passed, and finally the plasma stream arrived more than 13 billion kilometers from the Sun, in a boundary region known as the Termination Shock, where its speed abruptly reduced by half due to the external pressure of the interstellar medium. At the end of 2015, the shock wave reached Voyager 2, when the spacecraft was still inside the heliosphere, and only in 2017 arrived at Voyager 1, which had been sailing in interstellar space for 5 years. These encounters at the edge of nowhere have only recently become known to us, since we were able to process the data that the spacecraft had provided to transmit to us. But the most important thing, the real news, is another. From that same data, we learned that 13 days before Voyager 1 recorded the arrival of the shockwave, and 30 days before Voyager 2 did the same, the two probes had detected the unexpected arrival of a huge flow of electrons. In practice, it was as if the shockwave of plasma, once arrived in contact with the interstellar wind that came from the opposite direction, had suddenly accelerated its electrons to push them towards the two probes at speeds close to those of light. A very strange thing indeed. The idea that shock waves in certain conditions can accelerate the particles of which they are formed is not new, only that until now this process had never been observed, only theorized. And the extraordinary thing is that the phenomena has been detected directly in the interstellar medium, which is a very different environment from that of our solar system, both for particle density and for the lack of physical collision between the solar wind and the interstellar wind. In fact, as the authors of the paper reporting the news, published in Astronomical Journal, point out, this interaction between shockwave and interstellar medium seems to accelerate the electrons, pushing them forward as if they were messengers of what was coming. As a result, as has been calculated, the energized electrons begin to move about 670 times faster than the shockwave that originally pushed them towards the heliopause, meaning that they are accelerated to near relativistic speeds. Basically, it's like seeing light reflected from the glow of a distant explosion and then hearing the sonic boom come in later. And in this case, the time interval between light and sound provides important information about the properties of the interstellar medium and the penetrative capacity of the shockwave in the interstellar medium. The discovery could help physicists better understand the dynamics behind shockwaves and cosmic radiation coming from stars that can suddenly change in brightness due to powerful plasma emissions on their surface. To this dangerous typology of stars belongs also Proxima Centauri, the red dwarf sparking interest within the SETI program. It would be important to consider the physics of such phenomena when sending astronauts on extended lunar or Martian excursions, for example, during which they would be exposed to concentrations of cosmic rays far greater than those we experience on Earth. However, more data will be needed to better understand these results, especially from Voyager 2, which experienced this particular phenomenon when it had not yet left the heliosphere. And to tell us something definitive will surely be in the future NASA's IMAP mission, Interstellar Mapping and Acceleration Probe, whose launch is scheduled for September 2025. For the moment, we can only count on the precious collaboration of the old Voyager and the increasingly feeble messages that still come to us. How long will the probes last? But at this point, it becomes impossible not to ask the question, how long can Voyager last? And in fact, the situation does not appear rosy. The main problem is obviously the energy. The probes travel thanks to 3 radioisotope thermoelectric generators that produce energy using the heat emitted by the natural decay of radioisotopes of plutonium-238. The same type of generators also used, among others, in the Viking, Pioneer, Cassini, and New Horizons missions, but also during the Apollo 12 mission. The decay of plutonium atoms provides a truly enormous range, but plutonium also wears out over time. It is estimated that the probes have produced about 4 watts of power less each year. Therefore, the generators provide about 40% less power than they produced at launch. The energy is obviously used to run the onboard systems and scientific instruments, but not only. It is, in fact, also used to keep the instrumentation warm. This is why the engineers of the mission, after careful discussions and in agreement with the scientific team, have decided to intervene. In order to maintain the activity of the probes as long as possible, it is necessary to rationalize the use of energy, and it becomes strategic to choose carefully what to continue to work and what instead to cut. Voyager 2 took precedence in this plan, having one more instrument and therefore also consuming more energy over the years. Among the first actions already put into practice is to turn off the ultraviolet spectrometer, and recently a heater on the cosmic ray detection instrument, but not the energy to run it. In fact, the instrument plays a crucial role in detecting the amount of cosmic rays in interstellar space, information of vital importance for future human missions of space exploration. The problem of radiation is in fact the main problem for long-duration missions, such as those that humanity is going to undertake. What just cannot risk to be left at the mercy of the cold is, for obvious reasons, the pointing system, which allows the probes to orient themselves in the right direction to send data to Earth. If the power fails or if the cold damages it, we can no longer receive data or even communicate with the probes to send new instructions. The challenge is to understand when to remove energy, which information will be more important, and which can be sacrificed, to continue to do science as long as possible with both probes. Even after we lose contact with the 2 Voyagers, they will still keep traveling farther and farther due to inertia, and from then on they will turn from observers and explorers into ambassadors of our species, indeed, of all the species on our planet. Designed at a time when space exploration was a dream, the 2 Voyagers left carrying scientific instruments and archaic computers, but also a message thrown like a bottle into the sea to tell anyone who might encounter them, "Hello, here we are. This is our nature and our culture." A bottle full of images and recordings of wind, thunder, animal cries, crying babies, literary texts, and music of all kinds. We will never know about them again, but they will be like 2 seeds let go in the interstellar wind. The Wall of Fire. As you can imagine, through the Voyager mission, we are discovering many new things. At times, they're quite unexpected. For instance, Voyager 2 has found that once they're past the heliosphere, the plasma that is out in space doesn't go down. It actually goes up in density by a large margin. The marked increase in plasma density is evidence of Voyager 2 journeying from the hot, lower-density plasma characteristic of the solar wind to the cool, higher-density plasma of interstellar space. It's also similar to the plasma density jump experienced by Voyager 1 when it crossed into interstellar space. This led scientists to name it Wall of Fire because it lies just outside the solar system. The Wall of Fire outside the solar system is caused by electromagnetic radiation, which is created by plasma and a local space environment full of raging magnetic fields. But while this was terrifying for the probes, it also proved that NASA was right to launch not one, but two probes to go and explore the universe. Because for all we knew, the Wall of Fire might just have been in one centralized location, than a place basically filling up the boundaries of the outer solar system. The Voyager probes are showing us how our sun interacts with the stuff that fills most of the space between stars in the Milky Way galaxy, said Ed Stone, project scientist for Voyager and a professor of physics at Caltech. Without this data from Voyager 2, we wouldn't know if what we were seeing with Voyager 1 was characteristic of the entire heliosphere or specific just to the location and time when it crossed.
Plasma, if you didn't know, is the fourth state of matter, and it was always known, or at least believed, that there was some outside of the heliosphere, as between the sun's emissions and the rest of the universe pouring things into deep space, it was basically pretty natural for it to be there. And when Voyager 1 first reached the point of interstellar space, it noticed some slightly larger levels of plasma, but it was Voyager 2 that showed that it was much bigger than anticipated. Plasma is very hot, and while the Wall of Fire is said to be somewhat colder than the sun's plasma it's dispersing regularly, it's still hot enough to mess with people and objects, which we'll be talking about later. But more importantly than that is that it's thick. This is well and truly a wall of fiery plasma, which means that if we want to get through this, we have to be careful in a whole host of ways. But more than that, it means that if there is this one wall of fire plasma in the universe, there could be many more, and that opens up a whole new can of worms for what we might have to do to explore the universe, and just survive it in the most basic of senses. Plus, we didn't expect this to be in such concentrations in this part of space, which means we were wrong in pretty much all of our assumptions up to this point about what lies just outside of our solar system. What else are we wrong about? What else have we not been able to understand about what's going on out there? Could we be missing something else? Lots of questions, ladies and gentlemen. As noted, there are many problems with this wall of fire, and one of them may just be how exactly this thing is forming. After all, scientists were a bit stunned by the density that the Wall of Fire exudes in interstellar space. But what might be even more surprising, though, is that Voyager 2 indicates that part of the reason the field of fire is so thick is that the heliosphere has a leak in it. This was discovered when the probe noticed that there were particles actually leaking out of the boundary of the heliosphere, which couldn't happen because of gravity and solar winds. But if it is happening in this area, it's possible that it's leaking the particles in other areas as well. The Voyager probes are on different sides of the heliosphere. One is near the front and the other is near the side, quite intentionally, I might add.
So if the sun is unintentionally adding to this wall of fire, then that means that this field can grow every single day, and every single year, and beyond. So who knows just how big this field could get? Potentially, it could get so big that it starts to affect the heliosphere itself. Thus, while many scientists are thrilled at what's going on right now with the Voyager 2's information, that also means that we need to be prepared for what could happen with this wall of fire as time goes on.
The discovery of the Wall of Fire wasn't the only thing that people at NASA were interested in when it was discovered. Instead, it was also the fact that there was new information given about the magnetic fields that were there in the outer reaches of interstellar space. You see, our solar system is held within a magnetic field that is comprised mostly of the sun's field, not unlike the orbits of the planets and such. Thus, when you get out of the reach of the sun via the heliosphere, it goes to the reason that the magnetic field would go off in a different direction entirely. In fact, that is what everyone at NASA thought before Voyager 1 and 2 proved them very, very wrong. At first, Voyager 1 pointed out that there was some odd directions in the magnetic field of interstellar space. Then, when Voyager 2 arrived on the scene a few years later, its readings proved that the magnetic field of the area was actually parallel with the one of the heliosphere, which is confusing quite a bit of people.
The universe is so vast that we need to keep exploring it, looking at it, and doing whatever it takes to learn as much as we can. Not just for knowledge's sake, but for the sake of humanity in the future. Our goal is still to try and explore the cosmos, and the more we know, the more we can prepare, the more we'll truly be able to survive and enjoy the final frontier. Communicating with the probes. As we have already mentioned, one of the most important things about these particular probes right now is that they are in interstellar space, meaning that they are indeed beyond our solar system from a certain point of view, and they're seeing all sorts of interesting things and helping us learn even more about our universe. But of course, that raises a very fundamental question in terms of science and distance. If the Voyager 1 and 2 are in interstellar space, how the heck are we communicating with it? Distance matters in communications, as we all know, and the farther you travel from a point, the harder it is to communicate. So since we're not talking about space, but outside of our solar system via interstellar space, how are we reaching the probes? The simple answer to that is the Deep Space Network, also known as the DSN. This is a series of radio antennae that work together to not just send signals into space, but receive the signals from the craft and even give it instructions on what to do next. Just as important, though, is this: the network of antennae are all over the world. Centers at each DSN site receive incoming information, then they send it to the Space Flight Operations Facility at the Jet Propulsion Laboratory in Pasadena, California. There, the photos and other data are processed and shared with scientists and the rest of us. Many think that it is caused by waves existing in interstellar space. More specifically, the waves are vibrations in small amounts of gas found in the near emptiness of interstellar space. The vibrations are also known as plasma waves. The waves themselves are able to be converted into a sound, but not one that humans can hear on its own, which makes it all the more important that the Voyager 1 picked it up. If we could hear the hum, it would sound like a single steady note, playing constantly but changing very slightly over time. Keeping communication alive is crucial to get recorded information back to Earth, where it is read and stored in online archives. Without the DSN, discoveries like the electron burst detected in 2020 would go unnoticed. Yes, you heard me right. I said electron burst. The bursts occur when cosmic ray electrons, fast-moving particles from far beyond the solar system, are pushed by shock waves generated by solar eruptions. The electrons then accelerate further along cosmic magnetic field lines to incredible speed, study team members said. The idea that shock waves accelerate particles is not new, corresponding author Don Gurnett, professor emeritus in physics and astronomy at the University of Iowa, said in a statement. But we detected in a new realm, the interstellar medium, which is much different than in the solar wind, where similar processes have been observed. Why does this matter? Simply put, the process to make these electron bursts is complex, and the results of them being shot into space, mixing with solar winds and other entities, make them able to be propelled through space at basically the speed of light. Physicists believe these electrons in the interstellar medium are reflected off a strengthened magnetic field at the edge of the shock wave, and subsequently accelerated by the motion of the shock wave, the University of Iowa said in the same release. The reflected electrons then spiral along interstellar magnetic field lines, gaining speed as the distance between them and the shock increases. While science is obviously what they're focusing on here, the fact is that these radiation bursts can go and hurt both people and our own planet. Radiation is bad when in the wrong type and doses, and as such we're trying to study them so that we can better be prepared for when we send more people into space, as well as putting more people onto places like the Moon, the International Space Station, and so on. So thus, this research, this look into the radiation, the bursts of electrons in space, and so on, is absolutely vital for us to know what's going on to be affecting us the more we're out amongst the stars. You see, the Voyager probes have been at this for decades now, And it seems that with each new year, they go and provide new data, new insight, and new scientific facts and probabilities for us to go and ponder and explore. There's no way that when they were launched all those years ago that the people at NASA felt that they would have discovered this much, and yet they have. With every find they make, they're able to go and provide us with a bigger and more clear picture of space and what awaits us as we try and travel through it. Mysterious sounds, new bursts of radiation, plasma firewalls, and other finds are just the beginning. Imagine if the probes were able to find something that could revolutionize how we think of space. Some would argue that they've already found it, and that's why so many are eager to study all the data that they have, all the pictures and audio readings they sent back, and more. They're going to keep flying and recording data until they don't work anymore. And you can bet that the people at NASA and beyond are hoping that doesn't happen for a very long time. Family Portrait. Did you know that Voyager 1 took pictures of the planets in the solar system? It was the 14th of February 1990. A trail of 39 grayscale shots with zoomed-in color insets of each planet assembled from another 21 color-filtered photos makes up the famous solar system family portrait. Even though Voyager 1 was still approaching the solar system's border, where the protective bubble of our sun's solar wind gives way to interstellar space, the family portrait gives us a feeling of the size of our neighborhood and that there is a great lot beyond it still to be found. The spacecraft was about 6.4 billion kilometers or 4 billion miles from Earth when it took the photos, and at that distance, even Jupiter appears as just a dot. Saturn's rings are barely visible, and Uranus and Neptune are just blurry smears. Earth is an even tinier speck, less than a pixel in the image, yet despite its humble size, our world is still the most beautiful object in the Voyager 1 family portrait. The pale blue crescent of our home planet stands out against the blackness of space, a reminder of the fragility and preciousness of life. Venus occupies only a fraction of a pixel, while Mercury is so near to the Sun that it is undetectable in the Voyager 1 images. Mercury is the family member who always manages to sneak behind someone taller just before the picture is taken. And Mars, like the person who blinks just as the camera shoots, has lost its slender crescent in the glare of dispersed sunshine. Pluto, which was still considered a planet at the time because we hadn't realized that dwarf planets were a separate category of object to which the icy little world rightfully belongs, also doesn't appear in the photo because it's too small and too dim to be visible. Thanks for watching. What did you think of this look at the Voyagers and both their missions, and what they have revealed to the world as a whole from the depths of both our solar system and interstellar space? Do you feel that these are some of the most important tools we have in regards to researching space as a whole? Let us know in the comments below. Be sure to subscribe, and we'll see you next time on the channel.